the idea here is if we have a problem like this, it's a simple analysis. I have 6 samples for a cheese that is 30% fat, 6 samples for a cheese that is 25% fat, and so on. So we have 4 different products that we're trying to compare. Try to figure out how to make cheese feel the same in your mouth, taste the same with having a lower fat content. Wouldn't that be nice? If you're like me, you love cheese, but it's a high-fat kind of thing, and that's probably why pizza is one of my favorite foods, is there's just a lot of cheese on, the ones I'd pick out anyways. And it's funny to watch the kids go straight to the refrigerator. They know where the cheese is, and they'll put their hands in there. It's just a human instinct to eat cheese if you can eat cheese. I know not everyone eats cheese, but it's just one of those things. So it's a practical problem. You have some sort of measurement of these cheeses, and this one's called fracture stress, just like it sounds. Yeah, it's the strength that it takes to fracture any material. And in the food world, and I guess in the bioprocessing world too, we borrowed our methods for testing the strengths of foods materials from, actually one of the pioneers was in this department. He was like an international leader. He came from a mechanical engineering background where they were testing bridge strength and, you know, all sorts of structures. And he said, well, I can design some apparatuses that do that on food. So basically, what keeps cheese together for anyone in food chemistry? What keeps the structure together? Protein? Yeah, absolutely. So what kind of bonds are we talking about? Peptide bonds? Yeah. Maybe some disulfide cross-linkages. I think it's mostly going to be like hydrogen bonds and hydrophobic interactions. Yeah, so it's each one of those bonds has some sort of energy, kilojoules, that we have to break with fracture. And so there's a machine, I don't have a picture, but it basically tests how strong the cheese is. This isn't a food chemistry class, but it is a food and bioprocessing quality control class, so I think it's good to talk about other concepts from other classes once in a while. And so you see the problem here? We have 6 samples, 4 treatments, and we want to know, is there any significant difference here? So we have 6 samples, 4 treatments. Those 4 treatments are associated with one factor, right? What's the factor? Percent fat. So you know the difference between factor and treatment. We could have another factor here, like we do in the company's best yogurt example. In this case, we could have another factor that is like percent sugar or something like that, and that could have 3 treatments or something like that. So we have 6 samples, 1 factor, 4 treatments. And I don't know, I mean, this is a great example of the human tendency to get a set of data like this. And let's say you're the senior VP of R&D or something like that, and you get to choose whether you're going to roll out with this new product. And, you know, consumers are expecting a certain texture when they eat cheese, and these are the samples you get, and you're trying to make a decision. Did our way of making these different treatments, is there a significant difference between any of these? What do you think, just looking at them? Yes, maybe? So as we go up in fat, the fracture stress, which is basically a strength test, gets smaller. Makes little sense, right? Fat is not so strong. You can just melt it away and it just goes down to the dish of your plate or whatever. But the challenge is, like, how strong do you feel that there's a significant difference between any of these? One of them, the 15%, is twice as strong as the 30% fat one. Makes you feel pretty confident. But what if you were interested in the subtle difference between 25% fat, the second one, and 20%, that third one? So 15.67 versus 17. So you get the idea, right? Right now we're eyeballing it. We could make a decision, but that decision is just based on a whim. We're just going, yeah, I think it looks higher or lower, or maybe there's not a significant difference between the 20 and the 25, but there's definitely one between the first two and the third one and the fourth one. You know, you're just kind of guessing. And so that's the idea here, is that we don't make that mistake, because, again, the risk would be that you run a type 1 error or a type 2 error, a false positive or a false negative. The complications of making the wrong decision could be pretty severe. Wouldn't want to do that. So this ANOVA testing, I'm just trying to reiterate what Stephanie was saying, is what is it and why is very powerful but simple analysis that will keep you from making those type 1 and type 2 errors. And just take a minute as you're going through all this to think, what else could this be useful for besides cheese fracture stress? Maybe something that's more meaningful to you. Maybe you're interested in supplier quality. And so, you know me and my style. I like to kind of begin with the end in mind, instead of just mindlessly kind of going through each equation. I'm the kind of person who wants to know, how do we know we're done when we're done? So this is just another hypothesis test. You guys remember by now that we're going to reject the null hypothesis when the F, which we're going to get from here, not the best pen. Let's try a different one. Is greater than the F that we look up in the table. So we're going to look up the F table right here. You have access to in Moodle, or if you just Google F table, you'll find a bunch. This is for an alpha of 0.05, which basically gives us a 95% confidence. It's nice to feel 95% confident in life, right? Don't always feel confident, but with statistics, I think this is maybe why statisticians like their jobs, is they can feel confident. By default, let's just work with an alpha of 0.05, but you're welcome to assume a 0.01, because you want to be 99% confident. Yep. Okay. So we're going to work toward looking this number up in the table. So we're going to get some sort of number from this table and chart that, F alpha. And there's some sort of weird thing on the pen. F alpha, that's an A minus 1. A times n minus 1. Okay? So all I did was I tried to just show you how we're going to look up that value from the table. We're going to draw it right there on that normal curve. And we're going to take whatever this value is and figure out where is it. So if it's right here on this side of that F reference value, we're going to accept the null hypothesis, right? Where it says F for some alpha level, we're going to look up A minus 1 in the table and alpha times n minus 1. Now we have everything we need to look this up, right? Because we have F alpha, and then one number, and then another number. So that's where we're headed. So we'll get there eventually. Okay? So I just want to reiterate, it's a simple, once you get all the numbers calculated, it's just another hypothesis test. We start out with the null hypothesis and an alternative hypothesis. We're going to calculate the test statistic, and then we're going to compare it to the reference value. The only thing that makes ANOVAs more complicated is the math involved. And so eventually we need to get this test statistic. It's just kind of annoying because there's a bunch of steps we got to do to get there. It's just one of those cascading effects. So notice how we need to get the, and this will be familiar to some of you, the mean square for the treatment divided by the mean square for the errors. And in order to do that, we need to get the sum of squared for the treatment. So TR stands for treatment. T stands for total, which is right here. Okay? So it's one of those where it's, solve for one if you have two of the three. Pretty straightforward. So as long as you know what n is and what alpha is, and you keep that straight. And the most complicated part is when it comes to calculating the sum of squares. Sum of squares, that's some pretty funky stuff going on in those brackets, but I'll show you how to do it. So if we were to look at reasons for variation in a situation like this. Reasons for variation. We want to figure out how much of the variation is due to the treatment effects. And that's going to be, in all these formulas, we're going to call it TR, okay? And the other source could be just true error, or might think of it from the control charts unit as natural variation. And anytime you see it in these formulas, it's just going to be a big E, okay? So think of it this way, where the total variation is the sum of the treatment variation plus the error variation. So we're talking a little abstract right now, but we're just saying, if we go back to this problem right here, we have variation, right? We have a lot of variation. The average of the averages is 15.96. And if you just compare that to the individual treatments, there's variation there, right? It varies from 10 to 30 21. There's also variation amongst these samples. So there's just a lot of different reasons there could be variation. One could be due to the treatment effect. One could be due to just simple expected noise. In this case, we want to know how much of that variation is due to the treatment effects. Because if we compare the variation, and there's a lot more variation due to the treatment effects, then that's basically what we're doing here, is putting that into the test statistic calculation. So eventually, this is where we're going big pictures, the mean of squares. We're trying to compare how much of that error. Mean of squares is kind of a calculation. It just gives the idea of how much variation in this case is due to the treatment effects versus how much is due to the errors. The treatment effects is the percent fat in this case. Mm-hmm. Yeah. Yep. Yeah. Okay. So that's where we're headed. So I have a few slides that should help us get through it, and then I'll show you how to do this with this set of data. So we have n minus 1 So that's going to be 6 minus 1, which is 5. And then A is 4. Yep. So 5 times 4 is 20. Yep, perfect. I agree. And this is how you can do a quick little double check. Okay, and the mean squares are equal to the sum of squares divided by degrees of freedom. And all of that work to get one darn test statistic, which is f sub 0 in this case. Okay. Yep, another question?
What does the square mean? Like, when you're talking about the mean square or the sum of squares?
What does the square mean? Yeah, awesome question. I love it, because each of your questions is like introducing the next slide. To do the calculations for the sum of squares, where did it go? You see how squared right here? So we're going to sum, or see how we have the summation sign here on both equations. We have at least one summation. So we're going to sum and then see how the observations are squared. Yeah, that's a great question, because it really does, in this case, it is pretty intuitive. Bree?
Can you write that out, what it looks like for this problem?
Yes, I will. I have it on a slide coming up. I'm trying to build some suspense here, and I think it's working. Okay, so, and let me try saying one more thing. So now you understand why we call it sum of squares, because Chris asked the question. That was very good. Why did we call it the mean of squares? MS. If you look at this formula, we're taking the sum of squares and dividing it by the degrees of freedom. So we're trying to average out the squares according to how many there are. So for the treatment, there's 4 minus 1, you know? So I don't know if that helps a little bit. It'll help you if you're ready for this lesson, if you have some experience with this. If not, it might be like, whoa, man, you're blowing my mind. But we have the sum of squares for the treatment effects, and there's only 4 treatments in this case. So the way degrees of freedom works, it's just kind of weird. We subtract 1, so it's 3. But we're trying to divide out the sum of squares so that we could get the mean of squares associated with the treatment. And same thing with the error. Okay? Okay. So if you look at an ANOVA table, now you have enough information to interpret one of these. So most of them come right out of the computer. They say this is the treatments, this is the errors, this is the total. So this row has the sum. It'll be a number there. It'll be a number here and a number here. And it's just showing you the raw data so that you can figure out test statistics. So if you didn't have this last column, all you would have to do to get the F test statistic is divide the mean of square treatment divided by the mean squares for the error. So I'm just telling you because it's sometimes good to look at these ANOVA tables to make sure the computer's doing what you want it to do. The best way to double check it is going to be with the degrees of freedom, because if you have a set of data that has 4 treatments and 6 samples, you're going to be able to double check that the computer calculated degrees of freedom correctly, right? Now that I gave you the formulas, you would go, well, the computer says 3. Did I really have 4 minus 1 treatments? Yes. If the computer says there's like 20 treatments, then that gives you an idea that you have your data organized a little off. Okay, so first of all, just notice that what I've already done for you is I've calculated the totals. You know what a total is. It's simply 7 plus 8 all the way to 10. That gives us 60. And this 383 is the sum of all 24 of these observations. We have the average of the 30% fat, the average of the 25. So you see how this goes. And this bottom right one is the average of averages. So we should have everything we need to solve the problem. So here, all that suspense to show you how to calculate it out. For the sum of squares for the total, we're going to focus on, let's focus on what's in the parentheses here. Okay, so we're going to focus on how did we get all of these numbers. So we're going to sum the squares. So y refers to each of these as a y. Remember, This is y11, y12, y13, y14, y15, all the way down to, here's y41, y42, y43, okay? So we're going to square all of those. Notice the summation says, the first summation says we're going to take all of them from the first treatment to the fourth one. You know how to read sums, right? And we're going to sum the first sample all the way up to the sixth sample. So in this case, when you write out the summations, it's really annoying because here we're working with I and J instead of A and N. Doesn't that just bother you? You'd think mathematicians could get together and have a conference on the international standardization of like what they call things, but it just drives me nuts because you'll see in one book. So I could teach you with only A's and N's again, but I'm trying to tell you, if you got out there and you were trying to work with I's and J's, you'd just be confused. So, but anyways, we're gonna sum all 24 of those. So there's 24, right? Okay. So 7 squared plus 8 squared plus 15 squared plus 11 squared plus 9 squared plus 10 squared all the way to 20. So if you were to add all those up, it's going to be 383. Okay? And now we just need to subtract this term, 383 squared divided by 24. Where did that come from? If we go back to this one, that 383 squared divided by, again. So here we have, that's the total, that 383, which was right here. So we're going to subtract this 383 divided by 24. How am I doing so far? I think if I leave it here and let you kind of wrap your mind around it, since you have the table in front of you, you can match things up. So pat yourself on the back. Now you kind of understand at least how to get the sum of squares total. And now we need to get the treatment effect so that we can solve for the sum of squares with the E. Okay? So the good news is we don't have to calculate the thing that gets subtracted again. It's the same. We need to, and the other good news is it's not near as much math. We need to take the sum of squares for each of the treatments, from 1 to 4 treatments. So we're only going to have 4 numbers here. So we're going to take the first treatment sum of squares, squared, divided by 6, plus the second treatment sum of squares divided by 6, until we get to 4. So see right here we had 6 times 4 up here with the summation there. That means we're going to have 24 things that get added up in here. But right here, since there's only 4 things that we're summing up, we only have 1, 2, 3, 4 calculations. So if I go back to the data table and we try to figure out where did 60 squared come from, where did 94 squared come from, where did 102 and 127 and 6 come from, this is our sum of squared here. 60 squared plus 94 squared plus 102 squared plus 127 squared. So we're going to divide each of those by 6, and we're going to subtract this number. And if you do the math, we have 382.79 as the sum of treatment squares. How are we doing so far? Is your mind ready to explode? It's pretty tedious. It's harder than it looks. But I think it's good to just kind of walk through it like we are right now. So then it's a simple solve for sum of squares E. So pretty simple math at the end of the day. It's like control charts. We just got to figure out what to put in the numerator, etc. So just following with the formulas, for the mean squares of the treatment, we're going to put what we got for the sum of squares. 382.79 was right here. Okay, and then the denominator is 4 minus 1, because there were 4 treatments, and the degrees of freedom is going to be 4 minus 1. So we do that math and get 120, and then the same thing for the mean of squares error. We're going to put the sum of squares error in the numerator. And you have these formulas on the sheet that I handed out today. Divided by the degrees of freedom associated with errors, and we get 6.51. So if we divide, like our formula, where did it go? Right here says, to get F, now we have, so we started out, we had that top right part of the puzzle, sum of squares for the treatment, and then we got the bottom right. And now all we have to do is divide the mean squares for the treatment by the mean squares for the error, and that will give us F. Everyone see where we are? So we're almost there. So if we do that math, we get 19.61, which if you see that for any type of hypothesis testing, that just feels like a big number. We've been down this road before looking up t values and z values. That's a big one, 19.61. So we haven't looked up the critical number yet. It's 3.1. It's on the slide there. Oh, you caught a typo. Thank you. Yeah, everyone see that? There's a typo here. So it should be 127. Okay. I'll update that right now if I can. Come on. Oh, I can't. It's a screenshot. Okay, I'll update that after class. So now we need to figure out how to get this critical value of 3.1. Using an alpha of 0.05. And you guys know where 3 and 20 come from now, right? We went through that a few minutes ago. 3 and 20. So here we have this value. Okay, so we're going to, that first number is going to be in these columns here. So in our case, it's 3. Because this is the way we write it. It's just a convention thing. 3 right here and 20 right here. We had 4 treatments, and this number is 20. Okay? So we're going to go down 3 until we hit 20, and we get 3.1. Everyone see how I did that? And if we were to draw that out, we have a distribution where, let's say 3.1 is right here, and this value is way over here, 19.61. So are we going to accept or reject the null hypothesis? We're going to reject. Yep. As long as you know how many treatments there are, how many samples there are, and you can keep all those sum of squared calculations together. It's pretty tedious. It's easy to make a simple mistake, but you can do it.